One type of problem that's going to be increasingly important as we proceed through the course is going to be mechanistic problems. And this can be a pure mechanism problem in which I've defined for you the actual products that you are trying to make as well, but it also can be a predict the products as well as a mechanism type problem. So I could give you this problem as drawn, take this, add methanol, see what you get, and tell me why you get it. Or alternatively, I could give you this problem. When you mix this starting material and this solvent together, you end up forming both of these two products. Explain why. Regardless of your task, whether it's to predict or just simply to describe why this is happening, what I would want you to do is to look at this and size it up and realize, hey, this is probably going to be an SN1 type reaction because I have a secondary with a good leaving group, but I have a relatively crappy nucleophile, and I have a polar product solvent, which is probably serving as the nucleophile, and you can definitely tell that it's serving as a nucleophile by examining the products if you had them, but even without that, you would predict that you would be doing this sort of thing. Therefore, this is probably going to be an SN1 because everything I just talked about is at least biased toward SN1, except maybe for the only secondary part. But in any event, if you're thinking SN1, then you realize that this has to happen first. But now in a mechanistic problem, all of the details are about figuring out what is the order of operations and so on, and whether this is equilibrium or not. So the bromine leaving on its own will absolutely be an equilibrium step. This first arrow as drawn says that this carbon-bromine bond is becoming a lone pair on the bromine. The bromine originally had 3 lone pairs on it, now it has 4, therefore this has become minus charged. Since it has become minus charged, I must have generated a plus charge at the same time because this neutral thing decomposed, and therefore it needs to be neutral overall. So if I make a minus, I have to make a plus. If I make a plus, I have to make a minus. This is an equilibrium step because those two are clearly attracted to each other, so the most likely scenario is that they will simply recombine and go back the way they came. All of these things are happening. But in addition to that equilibrium step that is clearly taking place all the time, you also have plenty of methanol serving as a solvent. So there's lots of it around, and you can invoke this as many times as you like in the mechanism. So if you take a pair of electrons going from that relatively bad nucleophile, but one that's already solvating this molecule, it will go and create a new bond to that carbocation. This too you would expect to be a equilibrium step, because if you are making a bond, it's eminently possible that this could decompose back to the starting materials. This will end up forming 2 products at the same time, and that is because this material right here is flat. This is trigonal planar. This carbocation is in fact sp2 hybridized. That is because at this location is a hydrogen that's lurking there already, and it was the hydrogen that was back originally formally in the original starting material. But once the bromine has left, then this becomes trigonal planar and sp2, which means it becomes totally flat, which means the methanol can now attack from either side, either towards the camera or towards me, and that will then lead to a mixture, a 50-50 mixture of products at this stage. Now notice that neither of those products is where we're headed, but you can also imagine how you're going to get there in one more single equilibrium step, and that is if you invoke the presence of another methanol, which is going to be floating around nearby. Again, since the methanol is solvent, we can invoke this as many times as we like, and this will come by and deprotonate at this stage, which will cause the OH bond to become a lone pair on the oxygen, and that then explains the formation of both of those products 50-50 as the ethers. So the whole point of a mechanistic problem like this is to walk through what happens in what order and why. And so the idea is that first the bromine needs to leave, which then creates the planar intermediate that can be attacked from either side, which will eventually lead to the stereochemical outcomes observed. But in the interim step, you don't get there directly. You have to go through this protonated intermediate first, which then must become deprotonated by some base, which then leads to the final product. And everything along the way is subject to interrogation and analysis. You had a neutral thing. When the bromine leaves, that creates a plus thing. Therefore, the bromine needs to be around nearby because the bromine carries the minus charge. So this is balanced so far. I haven't drawn the bromine here, but it's still along for the ride. It's not doing anything. It's just kind of floating along. So there it is. And likewise, we're going to end up having some leftover bromine when all is said and done. That's just going to be floating around right there as well. Meanwhile, this was neutral formally, but the methanol specifically attacked the positive cation. Therefore, it leads to a positive thing. These two combine, so it leads to one positive thing. Then a methanol comes by and deprotonates, which leads to these potential neutral things, but that means that we need to have something else floating around nearby that bears a positive. Again, just as a means of controlling for the charge, which must remain balanced throughout the entire process. So in any event, the key parts of this reaction mechanistically are here, and this is also necessary if you're interested in trying to balance things. Another interesting consideration to think about is why the bromine, of course, does not do the deprotonation at this step. It is minus charged, and it could potentially do this deprotonation as well. But the problem with that thought is that bromine is the counterion of a strong acid, and therefore it is relatively unlikely to remove this proton. The pKa for this proton is on the order of -2, the pKa for the bromine is on the order of -9, therefore it is extremely unlikely to remove that proton because it's 10 to the 7th in the wrong direction. Whereas the methanol abstracting this proton leads to something that's -2, and again this was -2 to begin with, so this is essentially neutral. And so if you were to draw this all out and invoke the bromine doing the abstraction of that proton, that would be a mostly correct answer but not fully correct. For a fully correct answer, you would need to invoke a more plausible base, and that then leads to the final product. All of these details are what makes up a mechanism problem.